Thank you. So it's great to attend this Backstage user meeting. Actually, it was the first time, even though I have used Backstage for many years. And many of the talks about the process steel making. So I'm going to show another example, solid oxide cells. So solid oxide cells is a device which can convert either electricity to hydrogen or vice versa. The principle is it's quite simple. So the core part is this sandwich structure. So we have these two electrodes, anode and the cathode, and then in the middle that's the electrolyte. This electrolyte conducts only the oxygen ions. So we can use it for hydrogen production nowadays. This power to X is quite hot. So in this mode, we provide steam into the cathode. Then the steam is being split into hydrogen, and then oxygen ion transport the other side. And the same device can also be operated in the fuel cell mode. So when we have hydrogen, then we convert into electricity. So it can be used for power to X and also grid balancing, these kind of applications. So since we are using oxide, so we are operated at quite high temperature, 750 to 850. And this high temperature improves the efficiency, but also brings quite many chemical reactions, phase transformation. This is where CALPHAD and the Backstage can be used. And one cell only provides this 1.4 volts, so it's not for real application. So in reality, so here just an example of the exact reaction. So in fuel cell mode, we produce hydrogen, then react with oxygen, forming water and the electrons. The electron is released to the external circuit. On the cathode side, oxygen is being reduced. So the overall reaction is we provide electricity and heat. That's a fuel cell mode. And then in electrolysis mode, the entire reaction just reversed. So, and for real application, we need to stack them, a number of cells together, forming a stack. So we have the cell component. Then to prevent hydrogen and oxygen mixing, then we have to add this interconnect. And it conducts the electrons, but also separate hydrogen and oxygen. And when it comes to real stack configuration, we have to also consider how we distribute the hydrogen and oxygen. And so we have these different gas channels. So this is more complicated. Yeah. And over the years, we are developing the technology. We try to reduce the temperature from originally 1000 degrees C to latest 550 degrees C, and also to improve the current, improve the efficiency and the current. And we have used the different electrode materials. And for example, in the middle, the electrolyte, that's why I say yttrium stabilized zirconia. And for the fuel electrode, that's always a mixture of the nickel metallic nickel with YSA. So we call this ceramic. And on the oxygen electrode side, that's a perovskite mixture with YSA electrolyte. And so this just give you an SEM image, how the cell looks like on the in the micro scale. So we have the electrolyte, that's 10 micrometer 6. Then we have the porous electrode. So this is a hydrogen electrode. So metallic nickel mixed with YSA oxygen ion conductor. Then on the oxygen electrode side, there's a perovskite oxide mixed with YSA electrolyte. And the reactions happens at we call this triple phase boundary, where the electronic conducting phase, for example, nickel, and the ionic conducting phase, YSA, and the pore phase meets. And we have done this CALPHAD modeling for quite many years. So what our task is mainly to develop a thermodynamic database and also try to model the interface reactions and understand why the cell degrades. I will show you some real example. And yeah. So we have actually developed this, for example, this lanthanum strontium manganese oxygen and database, and also there are other research work groups working in this area. Unfortunately, this is like a small area, so solid oxide cells, it's not like the entire steel industry, so there are a lot of groups, a lot of people developing, so here is only a few groups developing the database. And so now I show you some real examples and what happens in solid oxide electrolysis cell. So when we use this for hydrogen production. So the cell voltage is kind of a monitor for efficiency and degradation. When we operate the cell in electrolysis mode continuously for hydrogen production at different current densities, so the cell voltage will increase, meaning the resistance will increase and the efficiency will decrease. And this degradation is related to the current density. So how fast we produce hydrogen. Of course, we prefer like a higher current density, so we can produce a lot more hydrogen in fixed time, but the cell voltage decreases very fast. So you can see it reaches like 1.8 volts in less than 1,000 hours. We are targeting like a lifetime of 5 years, so this is too much. And we try to understand why, what happens and why it happens. And we look at the microstructure. So this is a microstructure of the nickel electrode. So it's a mixture of nickel and YSA phase. So, and the black phase is pore phase. So you can see after this operation, so they detach nickel, and nickel YSA, detach from each other. And if we look at the fracture cross-section, so we can see why it detached, because on the nickel surface, they form a lot of these nanoparticles, like a push away nickel from each other. So, and destroy this nickel percolating network and hinder the electron transfer. And so it's like the cell is not able to operate at higher current density. So we try to understand further, and we did further TM analysis. So this is nickel particles, and this is a YSA phase. So we think that like the reaction starts from here, then extend. And we did the TM analysis, the composition of these nanoparticles as compared to the bulk YSA phase. So for the bulk YSA, it has a zirconium-yttrium ratio of the 4.2. And if we move to the interface, it has a higher yttrium ratio. And if we move to the nickel pore surface, it has less yttrium. So it's like something, the reaction happened at this interface, and zirconium diffuse either from surface, we believe most likely, or from the bulk, then form these nanoparticle, oxide nanoparticles, then push away. And it can also precipitate at other interface. So then we try to use thermodynamics to understand this. And we used, this is the first time, like it was 10 years ago. Yeah, we use a simple nickel zirconium oxygen in phase, and we calculate at what condition pure zirconia can be reduced. So it has, you can see it at a very low oxygen partial pressure. This cannot be reached in our electrolysis cell. So this mechanism does not count. But if we look at the nickel rich side, so there is this small region where nickel, metallic nickel, can dissolve some zirconium if we enlarge this area. And you can see we can, at relatively, for example, 10 to the minus 30 bar, we can already dissolve quite significant amount of zirconium into nickel. Then when we release the current, this zirconium can precipitate out as nanoparticles. So this could explain what happens in our solid oxide electrolysis cell. And so this is the first step. Yeah. And so we propose this mechanism. So on the operation, under certain conditions, in our electrolysis cell at this interface can become very reducing. And once it reaches the threshold, this zirconium will be reduced. Then either through the bulk or surface diffusion, then precipitates out at other interface. And if it at the nickel-nickel interface, it will push away nickel. And so this kind of explain what happens and also provide ideas for us how to solve this. And we are still trying to understand how zirconium diffuse through this surface or interface because we don't have a direct evidence. Then we also found something along with this. After this operation under hash conditions, we found that the nickel is not clean. So you can see, so this kind of nickel clean particles, but after hash conditions operation, we have these black dots inside nickel particles. And we did SEM EDX analysis. We found that, of course, we have the nano-zirconium particles at the interface, but inside nickel, we have silica. I think it's indicated here. Because we are doing steam electrolysis and we are providing system with hot steam, 800 degrees C. This will bring a lot of impurities into our electrolysis cell. So this could happen, but why it diffuse into the inside the nickel? Again, here we use the FACSH to calculate nickel silica oxygen system. So it's kind of similar, but it can happen at much higher oxygen partial pressure, more relevant in our real SOEC. So you can see it can happen already. So under this condition, the silica can deposit and dissolve and reduce into nickel. And and when we remove the current, then this silica can be reoxidized. So this is what we, again, proposed as a mechanism. So the silica comes from the steam and it can deposit at triple phase boundary, this reaction size as oxide. And if the interface is not reducing enough, it will just stay there, block the reaction size. And if under harsh conditions, this can be reduced and diffused inside the nickel. And once we remove the current, it will be reoxidized. So this is kind of indication of the severe degradation. So we use this as a tool to identify severe degradation. Now it comes to the oxygen electrode. Oxygen electrode is more complex to model because, for example, it's the oxygen electrode is this LSM, lanthanum strontium manganite perovskite. It's we have to use compound energy formalism with 3 or 4 sublattice, and we did it in thermocalc, but now we have a tool to convert the database into FACSH format. So when we have the LSM in contact with YSA phase, they may react with each other, forming this lanthanum zirconate phase, and this is not conductive. So we want to find out a window where we can avoid this. It can be either adjust the composition or adjust the operating conditions, like a temperature, oxygen partial pressure, or current. And we try to did this, and it's actually 2 PhD student thesis by me and my colleague Nicholas Grandi. And we eventually developed this 6-element database. And we did a lot of phase diagrams, so I will not show that. But what's really useful is once we have the database, we can predict the reactions. For example, with this composition, what will happen. So as a function of oxygen partial pressure. And so you can see when it's on the high oxygen partial pressure like air, it will be mainly the black one, that's Weiwei phase, and the blue one, that's perovskite phase. The phase we don't want is this light blue and this pink, strontium zirconate and lanthanum zirconate. This we don't want. So at high oxygen partial pressure, we are fine. But when we reduce oxygen partial pressure, they start to form. And so to reduce the degradation, we need to avoid this formation. And how this can be correlated to real SOC operating conditions. So we translate this into the operating diagram of the SOFC. So we have long-term test data, and we have observed after, for example, 1 year testing whether it forms this zirconate phase at the interface. And we put this into this diagram, temperature and the interface oxygen partial pressure. And this is the lines are calculated zirconate formation. So we can see it correlates quite well. So above that, that's kind of safe. And below that, that's risky. So this is try only consider the thermodynamics part. And we are doing this also with the kinetics part, taking into account manganese diffusion, these kind of things. Yeah, so this has to, we have to use Dictra or phase fields or micros. Yeah. So that's some example of the of the application in solid oxide cells. Yeah.
Thank you very much.